Okay, dear all, welcome to lecture 2. This is where we start off from lecture 2. Lecture 1 has already been done, so this is the second part of this lecture 2. So, like I earlier on explained, this gel has been cast in a vertical fashion. And normal circumstance, this gel is supposed to lie down. It's supposed to lie. But it's not lying. It has been cast in a vertical section. So you can see it is standing. And the sample is placed here. So, and one buffer section is here. One buffer tray is here containing buffer. Another one is here. And the gel is standing. We have others, and this is polyacrylamide gel because it is a very strong synthetic gel which is very robust, and most of the time it has a small pore size, and that is what is used in the chemical industries, Noguchi and other places, and it is very mutagenic. Mutagenic means that it has what? It causes cancer, mutation of the DNA. Very mutagenic. So often when it is used, safety precautions have to be strictly adhered to. Yes, so this is polyacrylamide gel. Agarose gel is from seaweed. So agarose gel is not so strong, but this is a synthetic, chemically produced gel. Very strong, robust, with a lot of cross-linking. Very strong, so you can cast it vertically, whereas seaweed, which is agarose gel produced from seaweed, has to lie down horizontally. So agarose gel has to lie flat on the ground, whereas this one is standing. So it's standing. Okay, so this is a component of a sample that has been separated. So you can see, we can say that this is what something like it contains gamma. You see the peak. Gamma is the smallest. So when you come here, the migration started from the top here. The migration started from the top here. No, honestly, I don't know where the origin is from, because it's not indicated in the diagram over here. So we assume that we don't know where the migration is from, but we just look at the concentration. You see that this one is very thick and deep colored. So you can say that it has the biggest proportion, or the biggest. It's not weight or mass or size, but it has the largest percentage among all these 5 components. We have gamma, beta, alpha 2, alpha 1, and albumin. So albumin is having the highest proportion, or the highest amount, or the largest amount among these 5 components of the sample, followed by alpha 2 and beta. Alpha 2 and beta of the same size, the same amount. So you can see over here they have the same amount. So you can see the peak is the same height, but gamma is shorter than them, and alpha 1 is far shorter. You can see, you can't even see the band. Whereas albumin has the highest and the most longest peak. Very long. You can see the wavelength. The peak is very high, so that is albumin. So this is one sample that has been separated into 5 parts, and of these 5 parts over here you can't see the constituent well. You can't see the constituent well until you come to the peaks, or the figure here. peaks. This is a wave pattern. So electrophoresis is usually done with gels formed in tubes, slabs, or on a flat bed. So this is a gel that has been cast in a tube. Previous one is a gel that has been cast on a flat. This is a slab. Okay. In most units, the gel is mounted between two buffer chambers. We all know the gel is mounted between two buffer chambers containing separate electrodes, so that the only electrical connection between the two chambers is through the gel. So you can see over here, the gel is between two buffer chambers, one buffer chamber, another buffer chamber. The electrode negative, positive, then the only separation is the gel. Okay, so let's see. This one has what? A sample well here, a stacking gel, and a running gel. And we can see that for a stacking gel has bigger pore sizes or bigger holes inside it than the running gel. So this one, the stacking gel, is just supposed to inhibit the movement of the sample or the particles in the sample. So the bigger particles in the sample will even move through the stacking gel. But because the running gel has a smaller pore size compared to the stacking gel, when the particles go through or travel through or traverse the stacking gel, the bigger ones get obstructed or prevented from moving through the running gel because the running gel has small pore size, but the smaller particles rather move through the running gel. So this one calls for what? Finer separations. The separation becomes very fine. Then at the end you get fine particles because the bigger pore sizes have been occluded or stopped over here. Then the bigger pore sizes are able to move through the stacking gel, but when they get to the running gel, they are stopped. So supporting medium, a gel matrix in which separation is done is called the supporting medium. Various types in use for separation, either in capillaries or on slabs, like I said, tubes or slabs. The gel matrix should be able to inhibit convection, and convection is defined as overheating due to remaining in the gel for a long time. So we say that the gel should be able to prevent overheating of the particles due to the particles staying in the gel for a long time. Then the gel should be able to prevent diffusion due to overheating of the trough or the container or the basin in which the electrophoresis is taking place. Then also the gel should be able, or the gel matrix should be able to allow permanent record of results through staining after run. And most of the time we use ethidium bromide to stain the gel. For polyacrylamide gel, you can stain before casting the gel. You add ethidium bromide to the gel when you are preparing it, when you are cooking it. But for for agarose gel, you only stain with ethidium bromide to visualize the samples after running the whole experiment. The gel provides additional separation through molecular sieving. Like I said, the gel has pores inside it, and the pores provide for what? Molecular sieving, meaning that it allows smaller particles to pass through and prevent larger particles from passing through it. We have two types of gel. We have the agarose gel, which is highly purified uncharged polysaccharide derived from agar. Later you will know what an agar is. Agar is like a starch. So that we cook. It's a powder we mix. In the video you saw the woman mixing a powder that she measured and put in and use water to mix it and place it in a microwave, cook it. Afterwards she made it cool. After the cooling, lowering the temperature, it became hard. Then she placed it on a gel slab and put it in the electrophoresis setup. So agarose gel dissolves when added to boiling liquid. It remains in a liquid state until the temperature is lowered to, so when you lower the temperature to about 4 degrees or below, it gels or becomes hard. The pore size may be predetermined by adjusting the concentration of agarose in the gel. So if you want the pore size to be big, then you lower the concentration or the amount of gel you put in the water and you cook. And if you want a smaller pore sizes, then you have to increase the amount of powder that you mix in the water, which you cook and later let it cool down before you put in the slab. So the more the agarose gel, the smaller the pore size, and the smaller the amount of the agarose gel, the larger the pore size. Agarose gels are fragile because they are from seaweed. They are organic. They are actually hydrocolloids, and they are held together by the formation of weak hydrogen and hydrophobic bonds. So this is the structure of an agarose gel. We have one here, one here, one here, one here, and it's formed of galactose, 1,3-beta D or dextrorotatory galactose, and 1,4-alpha levorotatory terraces and hydrogalactose. This is agarose gel. So this is the gel structure. The gel at a very over here, it is liquid or soluble state. So soluble state at 100 degrees. So when you cool it at 45 degrees, it becomes what? Solid. Then after becoming solid, when you let it remain and stand and cool more, it will become too solid, fibrous, very solid. And this is the structure of what? Agarose gel. So this is the structure of agarose gel. Polyacrylamide gel, this is a synthetic gel. It is produced only in the industry from chemical substances. They are tougher than agarose gels. Acrylamide monomers polymerize into long chains that are covalently linked by cross-linker. We will see that later. Polyacrylamide is chemically complex, as is the production and use of the gel. So this is the monomers. Monomer is what? 1 unit. 1. Polymer, more than plenty put together. So this is what polyacrylamide. So let me explain the diagram. This acrylamide, this is methylene bisacrylamide. So acrylamide plus methylene bisacrylamide, there is what? Cross-linking over here, and these are the acrylamides, and these are the bisacrylamide, methylene bisacrylamide cross-linking. So it makes the polyacrylamide very, very tough, and it has the smaller pore sizes compared to agarose gel, which you have to increase the concentration or the amount of the gel or powder to lower the size. So to prepare a polyacrylamide gel, determine the pore size you want. adjust total percentage of acrylamide, vary amount of the cross-linker, remove oxygen from mixture, initiate polymerization or chemical method. Photochemical method, like I told you, is a chemical method. Both make porous gels but differ in physical. Agarose and polyacrylamide gels make porous gels, make gels which have holes inside that particles can travel, but they differ in physical and chemical structures. A porous gel acts as a sieve by retarding, or in some cases by completely obstructing, the movement of macromolecules while allowing smaller molecules to migrate freely, like what I explained previously. By preparing a gel with a restricted pore size, the operator can take advantage of molecular size differences among proteins. So if you prepare a gel by restricting or controlling the pore size, you will be able to separate substances or molecules of different sizes, especially proteins. Because the pores of an agarose gel are large, agarose is used to separate macromolecules such as nucleic acids and large proteins and protein complexes, whereas polyacrylamide gel, which has smaller pore sizes, is used to separate most proteins and small substances, or when we say oligonucleotides, is what? Small DNAs. Both are relatively electrically neutral. Yes, polyacrylamide and agarose gels don't have any charge on them, but the polyacrylamide gel has a clearer resolution. It separates fine particles than the agarose gel, and is more suitable for quantitative analysis. So in Noguchi Memorial Research Institute, KCCR, Kumasi Center for Collaborative Research, that's for Tech, Noguchi is for Legon, and the Navrongo Health Research Center, they all use the polyacrylamide gel because it's better. They are supposed to use polyacrylamide gel, but polyacrylamide gel is very expensive, so they end up using the agarose gel. So these are the differences between polyacrylamide gel and agarose gel. Polysaccharides for agarose gel are extracted from seaweed, as I initially indicated. They are casted horizontally. Yes, they lie down. So polyacrylamide gels are extracted from seaweed, whereas agarose gels are extracted from seaweed, whereas polyacrylamide gels are cross-linked polymer of acrylamide crystals, so they are synthetically produced. Note these differences. You may meet it somewhere. Don't go and buy it to understand it. Okay, so agarose gels are casted horizontally, and like I previously explained, polyacrylamide gels are casted vertically. Agarose gels are from seaweed, so they are organic. They are not toxic or poisonous. Polyacrylamide gels can cause neurological breakdown. They are neurotoxic and can affect the central nervous system. Separation of large molecules. Agarose gels are used to separate large molecules. Polyacrylamide gels are used to separate small molecules. Agarose gels are commonly used for DNA separation, whereas polyacrylamide gels for DNA and protein separation. With the agarose gel, protein staining can be done before pouring the gel, whereas staining can be done after pouring out the gel for polyacrylamide gels. So let's look at what a continuous system is and what a discontinuous system is. A continuous system has only a single separating gel and uses the same buffer in the tanks and the gel, whereas in a discontinuous system, a non-restrictive large pore gel called a stacking gel is layered on top of a separating gel. Let me explain this. So, like previously explained, we have what? This is a continuous gel. It's a resolving gel, and these are the sample wells. but there is no, this is the only gel we have in a continuous gel. The difference is that with a stacking, with a discontinuous gel, initially the samples travel through a stacking gel. This is a stacking gel. The samples travel to a stacking gel with bigger pore sizes. The pore sizes are larger, very, very big than the normal resolving gel. So big samples can pass through this one, and two big samples are separated, but averagely big samples can pass through. But these averagely big samples cannot pass through the resolving gel because this resolving gel has smaller pore sizes than this stacking gel. So this one gives a better resolution. The discontinuous system gives a better resolution compared to the continuous system. Isoelectric point. A pH value at which there's no net charge on a protein is an isoelectric pH, or isoelectric point. We also call it isoelectric focusing. Above its isoelectric point, a protein has a net negative charge and migrates towards the anode in an electric field. I guess you understand this. If you do not understand, pause the video and think about it. You may now start the video again. Above its isoelectric point, meaning that anything above a pH of 7 is negative, because basic pH is negative. That's negative due to what? The hydroxide ion, or negative due to what? The formation of what? A conjugate base. So bases are negative. So above its isoelectric point, which is above the pH of 7, a protein has a net negative charge and migrates towards the anode in an electric field. And below its isoelectric point, the same protein is positive and migrates towards the cathode. So below pH of 7, the protein becomes what? It becomes acidic. It becomes an acidic. An acid has what? H plus, a proton, which is positively charged. So this positively charged protein will move to the negatively charged cathode. So the positively charged protein will move to the negative charged electrode or cathode. So this is the meaning of it. So let's see. So this is negatively charged particle or protein. This positively charged particle, you can see the positive charges on it. At low pH, it means that it's acidic. The protein is positively charged, whereas at high pH, which is basic region, the protein is negatively charged. So this is the movement. This is a positive electrode, negative electrode. So at isoelectric point, there is no net charge. Look at this particle. It has four positive charges and 4 negative charges. So there is no net. The net charge on it is 0, so it cannot move. The same applies to this. So this point of migration is called isoelectric point or isoelectric point. And the pH of the medium at which these particles are of neutral or they don't have any charge on them is called the isoelectric pH. So isoelectric focusing is a pH method. Is a method in which proteins are separated in a pH gradient according to their isoelectric points. Focusing occurs in 2 stages. First, the pH gradient is formed. In the second stage, the proteins begin their migration towards the anode if their net charge is negative, or toward the cathode if their net charge is positive. When a protein reaches its isoelectric point in the pH gradient, it carries a net charge of 0 and will stop migrating, as I explained. So this is isoelectric. These ones, all these proteins have been focused and they are at their isoelectric points. So this is a Kumasi blue. Kumasi blue method of staining is used for western blotting and those things, northern blotting of proteins and the rest. So let's look at them. These are just images. So this electricity part will not surface in your exams, so don't worry your heads over this too. Don't worry your heads over this. Okay, so we'll begin the next lecture. That's the last part of this lecture from here. Thank you very much.